Hello, I'm Michael O'Connell, and in today's video, we're going to calculate the fanning friction factor using Python code. Then we'll write code for additional functions to analyze two different situations. So the first situation I want to look at is one in which we are given a flow rate that we want to achieve for fluid moving through our pipe. This pipe will have a constant diameter, so there will be no change in velocity, so we can ignore this term here. Notice that I've written Bernoulli's equation in the head form, in which I've divided each term by the acceleration due to gravity. The utility of the head form is that each of these three terms on the left-hand side of Bernoulli's equation are in meters. So this gives us some freedom in terms of design for our pipe, in which we know what flow rate we want to achieve. Okay? We could have completely gravity-driven flow, or for us, we could supply a pressure difference through a device like a pump to achieve some flow rate that we want. So if we're talking about flow rate, we will need the velocity of our fluid moving through the pipe, which leads me to talk about this term here, which we've talked about before, actually just in the past video. And this is the frictional heating. We used this expression. I'll write the expression for the right-hand side. But during the last video, we were deriving the expression for the fanning friction factor for laminar flow. And we used this expression for the frictional heating. Now, obviously here, I have the acceleration due to gravity as well, because this is in the head form. So here we have a velocity that we need to get. Now, if we want to determine the head drop when we're writing the Python code for this function, we need an expression for the velocity, okay, because we've been given the flow rate. We need all these terms on the right-hand side, which isn't too bad, right? Delta x, so that's our length of the pipe. And then we have the diameter of the pipe, the acceleration due to gravity. So these are all things we know. And we'll write this expression for the velocity in terms of the flow rate that we want. Okay, so we know that the flow rate is equal to the velocity times the cross-sectional area. So this becomes pretty non-trivial from there. That's a really bad term there. Okay, and this, of course, would be embedded in that function that we are going to write very soon. And then we need the fanning friction factor. So that will actually be the first function that we write. So for that, we will have to look at a Moody diagram. And what I'll show you using Wikipedia is that many different people developed functions to describe the way the friction factor changes based on the Reynolds number and surface roughness of a given pipe. Okay, so those two factors I just said, Reynolds number and the surface roughness, are very, very important. So we'll need to write a function using one of the equations that has been developed in the past to get at this friction factor. So once we do that, we have everything defined on the right-hand side, and we can write Python code. We'll have a function that will spit out a result in meters, which will be the head drop that we need to enable the flow rate that we specify. Many people developed formulas to describe how the friction factor changes with surface roughness and the Reynolds number. In today's video, we're going to be using the Churchill equation, which is valid for laminar and turbulent flow. In the previous video, we developed an expression for the fanning friction factor for laminar flow, in which the value is 16 over the Reynolds number. And here we have the friction factor as 64 over the Reynolds number, and that is because this Moody diagram is based off of the Darcy friction factor, which is 4 times larger than the fanning friction factor. And these formulas that I have up on the screen from Wikipedia are also based off of the Darcy friction factor. Another convenient aspect with Churchill's equation is that we don't have to solve a nonlinear equation to get at the friction factor. It's just defined over here on the left-hand side of the equation. For us, because we're dealing with the fanning friction factor, we are going to multiply this value by 2 instead of 8 to get at the friction factor. Now I will proceed to write Python code for a function based off of the Churchill equation that will return the fanning friction factor. Now let's test this function to see if it actually works. Let's start by testing this function at laminar flow. So this would be at a Reynolds number below 2000. Let's do 1600 since the fan friction factor for laminar flow is 16 over the Reynolds number. This should be 0.01. So we'll put in some random surface roughness as well. And we do get almost exactly 0.01, which is good. Now let's go to the Moody diagram here. And let's try a Reynolds number like 1 million and a surface roughness of 0.01. Notice that this is about at 0.038 for the Darcy friction factor. So ours would be obviously that divided by 4. So let's see what that gives us. So if we do 1 million for the Reynolds number and then 0.01, we should get about 0.0095. And we do get about that number right there. So this is working properly, which is great. Now let's try to actually solve our problem by writing code for a new function that determines the amount of head drop we need to achieve a specific flow rate. Okay, so we will define that function here. We use HD for head drop, and then we want to have the flow rate Q, the length of the pipe, and the diameter of the pipe here. Okay, and we need to put in an expression for the velocity because that's on the right-hand side of Bernoulli's equation here where we had that frictional heating expression. Okay, of course, we're also going to need to use our function based off of the Churchill equation that has the fanning friction factor. And again, all those terms on the right-hand side need to be defined so we can find what that value is because that's equal to the left-hand side of our equation, which has all the terms that contribute or enable the flow of fluid through our pipe. So we need to know what head drop we need to achieve this flow rate. Okay, so we can express the velocity in terms of the flow rate that we want to achieve. Okay, and of course we have the diameter squared here in that denominator. Then of course we're going to need the Reynolds number, and that is going to be rho, where rho is going to be the density of the fluid that we're dealing with. And we'll multiply that by the diameter, and then of course by the velocity, and this is divided by mu, which is the viscosity of our fluid. Okay? And I don't know why it does that to me. Okay, and let's define some of these terms here. So rho, we'll say it's water, right? So 1e to the third, or 1,000 kilograms per cubic meter. And let me comment those units out. Okay, and then we have mu, which is the viscosity of water, which is 1 times 10 to the negative third Pascal seconds. Okay, and then the last thing we're going to need is the acceleration due to gravity because we are expressing everything in head form. And of course that's in meters per second squared. Okay, so let me just shift enter on all of these actually, just so that when we test this out it's actually going to be correct. Let's use lowercase f for the fanning friction factor, and we'll use what we have defined above. We have the Reynolds number, and then we have the surface roughness, of course, and then we can return the right-hand side of our equation. Now remember, we had 4 times the fanning friction factor, and then we had the term of the velocity squared divided by 2, so this whole thing can just be multiplied by 2. We can just do 4 divided by 2 there. And then this is multiplied by the length. And what else? We need the velocity. Okay, that's lowercase v. Don't want to get mixed up there. Now, when we divide this numerator, we need to remember that, as I said, this is in the head form. So we're not just dividing by the diameter, we also have the acceleration due to gravity down there as well. And we also need our function to take in the surface roughness because we're passing that through and we're using the Churchill equation function within the head drop function. Okay, so this should return the head drop in units of meters, of course, that we need to achieve some flow rate. So let's say we want to get a flow rate of 0.1 cubic meters per second. Okay, and we know some of these other parameters. So we know that the length of our pipe is 10 meters. We know that it's 0.1 meters in diameter. And then we know our surface roughness to be 5 times 10 to the negative third. We get 25.18 meters.
once again, this doesn't have to be an altitude difference. It can be a pressure difference, or it can be some combination of the two. For us, it has to be one of those two terms. It can't be a constriction that would cause an increase in velocity that drives our flow through our pipe because we have the diameter as a constant. Let's examine a situation in which we're given the head drop and we want to determine the flow rate. We encounter a problem because the velocity term appears in multiple places. First, the velocity appears in the expression for the flow rate, of course. Then it appears in the frictional heating equation, and it is also part of the expression for the Reynolds number, and the Reynolds number is used to determine the fanning friction factor, which is in the frictional heating expression. Thus, we need to solve a nonlinear equation to determine the flow rate given the head drop. So we can do that using scipy.optimize.root, okay? And we've used this solver before, and of course our function, the vector function we supply to the root solver, we will have a return, which will be an equation. And the root solver will iterate through flow rate values that will set this equation that we return equal to 0, okay? And then it will find that flow rate that makes that equation equal to 0, and we will have our answer. So let's see if we are able to do that. So I'm going to define a function for the flow rate, and this will accept the head drop that we know, and I'm going to call this beta. And then we're also going to need the length, the diameter, and the surface roughness. Conveniently, we already have a function that calculates the head drop with the volumetric flow rate accepted into that function, okay? So that is going to be really useful for us. Let's start writing code for the function that we want to supply to the root solver. So we can have some vector function here, x, and then of course we have to take, we're just solving for one unknown, so this will be the first element of that vector x. Okay, now what do we want to return? Well, we want to return a difference in head drops. Okay, so we want to start with beta, that's the head drop that we already know. And then we want to have the root solver iterate through volumetric flow rate values with this function that calculates the head drop until this head drop is equal to the head drop that we have for our pipe. And once it finds that volumetric flow rate that makes those equal, that will be the volumetric flow rate we will have for the head that we supply, beta. Okay, so we can put that right here with, of course, all of the same terms. And this, because scipy.optimize.root is used to solving multiple linear equations all at once, simultaneously, we will put this as a vector there, okay? And we should be good to go. The one thing we need to address is that this scipy.optimize.root needs an initial guess for the flow rate. So how are we going to determine that? That seems kind of tricky because we don't really have a way of guessing that just based on the dimensions of our pipe. And basically, we are only able to obtain an accurate guess for the volumetric flow rate by using the fact that the fanning friction factor has a very, very small range. So that will allow us to derive an expression that will be our guess for the initial flow rate.
An initial guess needs to be supplied for the flow rate. The fanning friction factor has a very small range of values. Therefore, an estimated value for the fanning friction factor can be used to calculate an initial guess for the flow rate. Let's derive an expression for the estimated flow rate. The head drop, expressed with the term beta, is equal to the opposite of the left-hand side of Bernoulli's equation. So the left-hand side of Bernoulli's equation, of course, is negative when we have a positive head drop. So what we want to do is set this equal to the opposite of the right-hand side of Bernoulli's equation, which is going to be the frictional heating, of course without the negative sign this time, divided by the acceleration due to gravity. So we know this expression, and we just have to remember to include g there. And here we can get rid of that and make this 2, and this will be equal to the head drop of which we know. We can get an expression for the velocity and use that to have our final expression for the estimated flow rate. So let's do just that. Let's multiply both sides by dg. So we'll get this expression here, and then divide everything by 2 times the fanning friction factor. We have our delta x in there, the square root. Now, what we want to do here is multiply by the cross-sectional area. So that would be pi times the diameter squared divided by 4. And this is equal to q sub g. We could call it, that is the estimated flow rate here. So that is what we will implement into the Python code, and then we will continue solving this problem.
Now that I've put in code for the estimated flow rate, I would like to comment on the fact that I also put in a guess for the fanning friction factor. I just did 0.01. Again, it's a very, very small range of values, so this is kind of in the middle if you look at the Moody diagram we were looking at before. So I think it will be a very, very good guess for our purposes here. And notice that this took a while to load, and that's because I haven't selected Shift Enter for all of our other pieces of code. And I've also not actually put in the root solver. I haven't gotten that yet from scipy.optimize, so I need to do that up here. Okay. And then I will make sure that this function works, and that will be the end of this video. So we've dealt with 2 different situations. The first situation was one in which we know the volumetric flow rate we want to achieve, and we need to see what head drop we need to get that flow rate. And then the other situation that we're going to test with our flow rate function is one in which we actually have the head drop, and we want to see what flow rate we will get through our pipe based on its dimensions and all of that. Okay, so what I'm going to do here is actually use this same head drop, okay, that we used to test this function up here in which we were determining the head drop. So I'll put that in there for a head drop, and then we'll use the same dimensions, and hopefully we should get about 0.1 for the volumetric flow rate, and that would be in cubic meters per second, of course. And we'll use the same surface roughness, okay? And we do get about 0.1, okay? So our function works, which is great. So if you had some situation in which you had a pressure difference and an altitude difference that is basically 25 meters in a head drop, you would get this flow rate. These calculations that we are doing are very accurate, and they're very useful for engineering applications. So I really hope that this video in which we've coded in these functions was very helpful for you. So I thank you so much for watching, and I hope to see you next time.